So today we're moving on to um, further into the unit we started the other day with Riemann sums, into the topic of definite integrals. So you'll notice your notes say BC. It's because I used, in this particular case, I don't always do this. In fact, it's probably less than half the time. But this is the same um, lesson that I used in my BC class. So if we have f that is a continuous on a closed interval function on a closed interval from a to b, and then we divide that whole interval from a to b into n subintervals of equal length. Now remember, with Riemann sums, we didn't have to break it up into equal length parts. But here we're going to, where delta x is b minus a divided by n. So n is how many subdivisions we have. B minus A is the width of the whole subdivision, or the whole thing. So then we take that and divide it up by however many subdivisions. Then the limit as n goes to infinity of the summation as k goes from 1 to n of f of c sub k times delta x, where c sub k is chosen arbitrarily in the kth subinterval, is the definite integral of f over the interval from a to b, and it's written like this kind of stylized capital S looking thing. Oh, is it not on?
Yeah.
I thought I hit it. Sorry about that. I must have hit a different button. And go. All right. So this sort of stylized looking, it looks kind of like a tall, skinny S. That's the integral sign. So we're going to have the integral from a to b of f of x dx. So just real quickly, a sketch. So you've got something like this. Yeah. So this is a, and this is b, and this is y equals f of x. So with the Riemann sum, we were like, if I want to divide that into n subintervals, it doesn't really matter how, if I want to divide it into 3 subintervals, I can divide them into any width I want, and I can pick any point I want. Here, we're dividing it up into equal width subdivisions. So I'm going to divide it into like 8. And I did that because you're just cutting things in half. The human brain is pretty good at cutting things in half. It sucks at cutting them into fifths. Okay? So then if I pick any place, notice that what's happening here is I'm getting all these little rectangles, and I'm just picking arbitrary spots in here. Morning, gentlemen.
Morning.
You see how I don't have the big gaps that I had when we did, the Riemann sum on the graph? And so what happens is that if we take an infinite number of those, then we can completely smooth out the top and make it follow the curve exactly. Okay, and that's what this is doing. It actually is finding this area underneath the curve. I liken it to, have you ever seen a digital image where it's not real sharp because it's very pixelated, right? It's so the way that you make it smoother is to have more pixels, right? And so each individual pixel is smaller. It is exactly the same thing here. What we're doing is we want to smooth out the top, and so what we need to do is have a whole lot of rectangles. But they're going to be so skinny that you can hardly tell that they're rectangles anymore. They're just going to look like little lines going up, and with those little lines going up, we can make a very nice smooth looking curve. The same is true on your calculator. Your calculator doesn't have any curves built into it at all. It's just a bunch of pixels. And if you want to get nutty, your TV's like that too, right? Or your phone. It doesn't have any curves on it. But you don't ever think about it being a bunch of, a bazillion little dots. But there's so many that you can't hardly tell, or hopefully you can't tell at all. So this symbol is the integral sign. Again, it looks kind of like a skinny capital S. A is called the lower limit of integration. It tells you where we're going to start our subdivisions. B is the upper limit of integration. That tells us that's where we're going to stop taking subdivisions. F of x is called the integrand. It's what we're taking the integral of. And the dx at the end tells us that x is the variable of integration. So hopefully these two are going to match. Later on, when you take like a Cal 3 class and do multivariate integrals, it's really important that you look at these two variables, because sometimes they're not the same and you have to treat them completely differently. Okay? For our purposes, they're always going to be the same. And for our purposes also, this is supposed to remind you that, notice here, we're multiplying the height of the rectangle times the width of the rectangle, right? That's what these two things stand for, the height of the rectangle times the width of the rectangle. That's from Riemann sums. It's the same thing here, except instead of delta x, this big clunky thing, we have dx, this tiny little sliver rectangle that is so small that it doesn't even hardly look like a rectangle anymore. And this is to remind you of this. And the reason that this looks kind of like an S is to remind you that it's a sum. Okay, there's some mathematical symbols where I'm like, I don't know why they picked that. There are some where it's like, it was all carefully thought out. All right. So if f of x is non-negative, meaning it could be 0 at times, but it's mostly positive, and integrable, sort of like differentiable is a word, integrable is a word. They're both very difficult to say early in the morning. Over a closed interval from a to b, then the area under the curve y equals f of x from a to b is the integral of f from a to b. That is, the area is the integral. That integral tells us the area under the curve down to the x-axis, provided that our function is integrable, and we'll talk more about that later, what makes something, a function, integrable, and it's non-negative. We'll deal with what happens when there are some negative values in just a second. This particular one, you're like, how am I supposed to do this? Well, at this point, all you're going to do for any integral that we do is you're going to think about it in terms of area. So everything that we do has some geometric formula that you can use to help you out. Now, the reason I did this one is because it's in a lot of calculus textbooks, and it showed up on an exam not too long ago. And I was really surprised because it hasn't in a long time. And it is very much what I call a light switch problem. Either you know how to do it or you're completely in the dark. And the reason why it's weird is because of this square root function. So let me just show you what that is the graph of. If I say, and I'm going to do this over here, y is equal to the square root of 16 minus x squared plus 3, and you're like, I have no idea what that looks like. Real quickly, you're going to remember what this looks like exactly. I'm going to subtract the 3 from both sides. And then I'm going to square both sides. And then I'm I'm going to add x squared to both sides. And I'm really hoping at this point you're like, wow, that looks familiar. You recognize that you recognize it. Do you remember what it is?
Circle.
It's a circle. That's exactly right. This is a circle, centered at 0, 3, with a radius of 4. Now, our original is not a circle. You're like, wait a minute, didn't I get this from this? Yep. The original is just the top half of the circle, because the y value is always going to be positive. The square root of a number is always going to be a positive, plus 3, also positive. So what does this look like? Well, we've got a circle centered at 0, 3. Its radius is 4. So it's going to look something like this. And that's handy because notice my limits of integration were from -4 to 4. It's cooked up so that you can do this without, knowing some sort of advanced geometric formula. And hey, look, I'm just finding the area. Well, it's a rectangle with half a circle on top. So that's going to be equal to the area of the rectangle, which is 8 by, oh, sorry, I didn't go quite down far enough. I'm supposed to go through there. So this is 8 by 3, that rectangle, plus I've got half of a circle, so half of pi times the radius squared. The radius is 4. So this is 24 plus 16 pi. We will learn some shortcuts for being able to do this for an awful lot of functions. Even after we learn all of them, that's not one of them. And that's why the nice people at the College Board put that on an AP exam, because they wanted to check, do you remember that this is an area? Now, they picked a really insanely difficult function, I think, to do it with, and I think you'll see one like that on a homework assignment. All right. Most of the time, the ones that you're going to be getting at this point are going to be rectangles or triangles or trapezoids, or ones that you can divide up into those things. Okay? Now, what if f has both positive and negative values on the integral from a to b? What we do is we count the area above the x-axis as being positive, and then we subtract the area below the x-axis. The temptation always on this is to say negative area, which is just dumb. There's no such thing as negative area. But we're going to, when we're summing it all up, we're going to count that as a negative contributor to the integral. But please don't ever say that it's negative area. That's like saying straight line in geometry. Just like, oh, please don't. All right, let's go on to page 2. So here, let's use the fact that the integral from 0 to pi of sine of x dx is 2, which is really weird. You're like, wait a minute, I have this weird trig function and I'm going from 0 to pi and it turns out to be exactly 2? Yes, it does. It's surprising, but we're just going to go on. Okay. So I'm going to draw that. All right. from 0 to pi, sine of x, that's the first hump, right, in the sine graph. This area is 2. Well, then it says, well, what would happen if I went from negative pi to pi over 2? Okay. So here's pi, here's negative pi, here's pi over 2. What is this area going to be?
Negative.
What is the area going to be? 2. Yeah, the contribution to the integral is going to be negative, but the area is going to be 2. And then what is this area going to be? 1. So this is going to be equal to positive 1 minus 2. It's negative 1. For this one, you're like, oh, sine of x minus 2. I got to remember some stuff from algebra and maybe pre-cal. What happens when I have that x minus 2?
Phase shift.
And which way does it shift?
To the right.
To the right too. Very nice. So now, that hump is going to be here, and we went from 0 to pi, so if I start at 2, I'm going to go to 2 plus pi, right? Oh, hey, look, those are the limits of integration. What is that area?
2.
It's 2. So this is 2. Again, everything is going to be, and I'm not doing a bunch of the rectangle problems and the trapezoids and stuff like that, but when you draw the diagram, if you have the top is something that's straight, you should be able to break it into pieces and find the areas of those pieces. So the integral of a constant, this is the only rule for definite integrals we're learning today, is if f of x is equal to c, where c is a constant, then the integral from a to b of f of x dx is equal to the integral from a to b of c times d of x, I'm just replacing, is that constant times b minus a. And you're like, well, why is that? Well, if I have a constant function, let's say this is 3, and I'm going from 1 to 5, I've got a rectangle, right? This is going to be equal to 4 because it's 5 minus 1. That's where this part's coming from. That's the base of the rectangle. And 3 is the height of the triangle. So there, the integral from 1 to 5 of 3 dx is 3 times 5 minus 1. It's 12. So the constant function is the easiest one because it just makes a simple rectangle. So that'll save you from having to spend time drawing it if you get one like that. All right. So here we have an example. A train travels along a track at a steady 65 miles an hour from 1 a.m. to 3 a.m. Express its total distance as an integral and evaluate the integral. Well, the integral would be the integral from 1 to 3 of this constant rate of change, 65 dt, because it's time. You could write dx. It doesn't matter because there is no variable in this. So that's going to be equal to 65 times 3 minus 1. It's 130 miles. Which, when you think about it, you're like, I didn't really need calculus to do that. No, you really don't. But what's going to be interesting later on is, well, what if this isn't constant? we can do the same thing. We can do the integral of the velocity is going to give us, over some time interval, is going to give us the change in position. It'll give us the displacement. So in addition to continuous functions, functions that are bounded on an interval, that means it doesn't have any infinite behavior, with a finite number of discontinuities. You can have a bunch of them, but it has to be finite. You can't have an infinite number of discontinuity. Those are also integrable. So this function, the absolute value of x over x, I like this function. All right, pick a positive number.
3.
Absolute value of 3 is?
3.
Over 3 is?
1.
1. Pick another positive number.
50.
The absolute value of 50 is?
50. 50.
Over 50 is?
1.
Is 1,
Yeah.
right? So for any positive number, this is always going to be 1.
Good.
Now what happens at 0?
0 over 0.
Which is?
Undefined.
Undefined. All right, now let's pick a negative number.
Negative 200.
The absolute value of negative 200 is?
200.
Divided by 200 is?
1.
Try again.
Negative 1.
Negative 1. So this is discontinuous. In fact, it doesn't even exist at x equals 0, but we don't care. We can still do the integral from negative 1 to 2. So if this is negative 1, this area is 2. This area is 1. So that's going to be 2 minus 1 is 1. All right. Grab your calculators. The fourth operation that you're expected to be able to use your calculator for on the AP exam for this class is evaluating a definite integral. Remember that the other 3 are graph on an appropriate interval in an appropriate window, be able to solve an equation. You have this thing equals that thing, be able to solve for the variable, be able to take the numeric derivative, and then this is the fourth thing. If you're using your calculator for anything else, you probably are not going to get credit for it if it's part of the free response questions, because you need to be showing work for that. Okay? All right. So first it says evaluate this integral. By the way, this is another one of the ones where I'm like, I don't think there's a way to do this even after we learn the shortcuts for being able to do these. But we can do that on your calculator quite easily. It's in the math menu. You can either scroll down to it or just remember it's math 9. Remember the definite integral was math 8? So our lower limit is negative 1. Our upper limit of integration is 2. And we're going to do x squared times the sine of x. And we're taking the derivative with respect to the variable x. I give TIs crap because there are some things where I'm like, TI just has, they've put out a product and they have made very few improvements to it over the last 20 years. This is something that they did do. It used to be that it was like programming language, and you had to know where to fill things in. They've made this much nicer. And you hit the button and you go, okay, cool. 2.246. So if you just need to evaluate an integral, you can do it from a standing start. It's just Math 9. Now, you can also do it from the graph screen. There will be times when, especially if you have to use a function over and over and over again, the best thing to do is to put it into y1 and then you can do whatever you need to it. So let me show you. If we go to y equals, clear out any crap that's there. 4 over 1 plus x squared is our graph. I do like that they've put in the horizontal fraction also. They should have done that ages ago. And I'll do as I'm required by law to do. No, I'm not. But the numworks calculator automatically does horizontal fractions. It doesn't do the slash fractions, which I think is terrific. All right, so I'm going to graph this in a standard viewing window, so I'm going to do zoom standard because I have no idea what I was on. So you have this, distant mountain function. I'm going to zoom in a little bit. I'd like to see it a little bit better than that. So I'm just going to zoom in at the origin. And okay, yeah, it kind of goes out, but I'm okay with that. And I want to get the integral from 0 to 1. So there are actually two different ways that I can do it. I can do it from the graph screen itself. If you do second trace to get to the calculate menu, notice right down there at the bottom, number 7 is the integral. You can either scroll down to it or just type the 7, and it asks you for the lower limit. It's already set at 0 on this one. And then it asks for the upper limit, which is 1. And it even shades it in for you, which is kind of nice. And it's 3.14159. It is pi. And we'll talk later on about why this is pi. More specifically, but generally speaking, before we do anything else, do you remember a derivative where we took the derivative and we got 1 over 1 plus x squared? What was that the derivative for? Tangent inverse. Yep. This has to do with tangent inverse. What's tangent inverse of 1? Pi over 4. The 4 on top multiplies that times 4 and it gives you pi. Again, you get things like this where you're like, wait a minute, that's just wild. Because you don't think about this as having anything to do with anything trigonometric or circular, even when you look at the graph and you're like, but the answer comes out to be pi. You can also do that from your home screen. So let's say you've already got that in. What you can do is do Math 9, do the integral from 0 to 1 of, it's in y1, and the easy way to get that is alpha trace. So whatever's in y1 goes in there, and we're taking the derivative or the antiderivative with respect to x, and I can get it that way also. That's nice because, like what if you had to do some manipulation with it, or if you needed the derivative also, right? I can do the derivative, do Math 8, the derivative with respect to x of, again, y1, evaluated at, say, x is 2. And it'll give me an approximation for the derivative at that point. So all good stuff.